All right, welcome back to chapter 3. So today we're talking about prime factorization. We talked about primes in the last section. So when we talk about factoring an integer, we write it as a product of integers. So we take the number 12, for example. 12 can be written as the product of two integers. Let's say 6 times 2. That's one example. There's other examples, but let's try 6 times 2. Well, 6 we can also write as a product of integers. So we can write 6 as 3 times 2. So we can actually write 12 as being the product of 3 times 2 times 2. Or to even put it a little bit shorter than that, 3 times 2 squared. All right, and that's known as prime factorization. 3 and 2 are both primes, so we can't factor it down any smaller than that. All right, so yeah, again, it's often written as powers like that. So I wrote it sort of backwards here. It's pretty common to write it in numerical order, so from lowest to highest. We can use a factor tree to organize our work. A factor tree would look like this. So we'd have our number at the top, so we have 12 at the top. Then we'll break that into two integers that would multiply to be 12. So in the case that we did, 6 and 2. And then if you reach a prime, you can circle that to know that you're done with that branch there. And now 6 we can break down further into 3 times 2. And these are both primes, so go ahead and circle these. And that's as far as you can go. Everything's circled, so now you know it's going to be 2 squared times 3. So knowing that, let's go ahead and give these a shot, and let's do the prime factorization for each of these numbers. Go ahead and give it a shot on your own. All right, so for 30, we'll do that up here, so we have lots of room here, so 30. So there's different ways you can do this. So if you don't do this the exact same way as me, that's okay. I'm just picking one way to do it. So let's do 2 times 15. That's one way to make 30. Well, let's see, 2 is a prime, so go ahead and circle that. 15 is not a prime. We can do 5 and 3. And those are both primes. Okay, so 30, prime factorization would be 2 times 3 times 5. No problem. All right, now how about 60? Okay, let's see. 60 would be 6 and 10. 6 would be 3 times 2. And we have 2 primes right there. 10 is 5 times 2. And we have 2 primes right there. And looks like we're done. So 60, how many 2's do we have? We have 2 squared times, we have a 3 and a 5. 3 times 5. Okay. Now 252. So 2, 5, 2. All right, well, let's see what we can do here. So it's an even number, so we know 2 is a factor. So 2 and 252 would be, let's see, 1, 2, 6, 126, if I did that right. 126. All right, and then, so we do have a prime right here. All right, and then this can be broken down here into 2 again. We know it's an even number, so half of that would be 63. And we can use our divisibility test to know that this would be divisible by 3. That's one option. How about 9? So if we add up these digits, 6 plus 3 is 9. We know it's divisible by 9. Then we say, oh yeah, that's right, we knew that. So 9 times 7 is 63. Okay, well, 7's a prime. And 9 would be 3 times 3. So it looks like we have all primes there. All right, so we have 2 2's, so 2 squared times 3 squared times 7. Okay, last one, 288. 288. And once again, we can do our divisibility test if we wanted to. So we know that it's even, so it would be divisible by 2. That's one option. Let's go ahead and go with that. Let's go with 2 times 144. Another option, if you found it, but with divisibility test, you would find that 9 times 28 would also work. For that, or sorry, not for that one. 72 times 4 would be another option here if you wanted to start with that. But anyway, so 144, we know that is again even. So we could divide by 2, but 144, I recognize that as a perfect square. That's actually 12 times 12. All right, and then 12 could be broken down into 3 times 4, or 6 times 2. And 4 is, of course, 2 times 2. All right, so prime, 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 and prime. I think we got everything here, all of our branches. We didn't leave anything. All right, looks good. So 288 would be, let's see, we have 1, 2, 3, 4 2's. So 2 to the 4th times, what else do we have? We have 3's. We have 2 3's. Oh, I think I missed a 4. 1, 2, 3, 4, 5 2's. 2 to the 5th times 3 squared. Anything else? Got 3 squared, got 2 to the 5th, and I think that's everything. All right. Cool. So those are those. So one note is that every positive integer is going to have a unique prime factorization. So every prime factorization for every integer will be different. You'll never find prime factorizations for 2 different integers that are the same prime factorization. So that's called the fundamental theorem of arithmetic. We don't have the tools yet to be able to do a rigorous proof of that, to be able to prove that all integers will indeed follow that rule. But it is indeed the case, and maybe later on in your math career, once you get into higher level calculus and things like that, then you might be able to prove that fundamental theorem of arithmetic. But for right now, know that it is safe to assume that every positive integer is going to have a unique prime factorization. You might think also, what about if you prime factor a prime? So if you have 5, what's the prime factorization of that? Well, that's just going to be 5. The prime factorization of 5 is just 5. Now, how about 1? So 1's a little bit interesting because what primes could you multiply together to make 1? Well, the answer to that is it just accepted in math that the prime factorization of 1 is just 1. So 1 is the prime factorization of 1. Now, is 1 a prime? It is not, but it is accepted that 1 is the prime factorization of 1. All right, so now we have a bunch of perfect squares, interestingly. So go ahead and see if you can find the prime factorization of these. All right, so we'll start with 16. So 16 is going to be 4 times 4. Or we could do 2 times 8. 2 times 2 times 2 times 2. Okay. So it looks like this is going to be 2 to the 4th. All right, how about 36? 36 would be 6 times 6, which would be 3 times 2 times 3 times 2. Okay. So we have 2 squared times 3 squared. All right, how about 81? 81, we have 9 times 9. And so you see this pattern here where the left side of this tree is going to be the same as the right side of the tree if you start with the square numbers that you would square to get to the number. Again, we didn't have to start with 4 times 4 to get to 16. We could have started with 2 times 8. We would have gotten the same prime factorization. And I can show that real quick. So 16 here, since we already did the prime factorization here, we started with 16, and we start with 8 times 2, and then we break this down to 4 times 2, and break this down to 2 times 2. We still get 1, 2, 3, fours, 4 2s. So that'd be 2 to the 4th, again, even though we did it in a different way. So anyways, but if you do it this way, you can see that the left side of the tree is going to be the same as the right side of the tree. So 3 times 3 are primes, and you know that the other side of this tree is also going to be 3 times 3, but we'll go ahead and write it out anyways. So it's going to be 3 to the 4th. Okay, so then this last one here, 144, is 12 times 12, and 12 is 6 times 2, and 6 is 3 times 2. Again, 6 times 2, and 3 times 2. For our primes, we have prime, 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 prime. So we have 1, 2, 3, 4 2s, so 2 to the 4th, times 3 to the 3 squared. Okay, so what do we notice? How can we use the prime factorization of a number to tell whether or not the number is a perfect square? So the answer is down here already, but if you haven't looked at that yet, what do we have in common of all of these prime factorizations of these perfect squares? And if you haven't noticed, which is not super obvious to notice, but these are all even numbered exponents. And so why does even number exponents, as long as everything is an even number exponent, if you have something like 2 to the 4th times 3 to the 3rd, well, one of these is not an even number exponent, so you can't do that. You know that that's not a perfect square. But for all these are all filled with only even number exponents. Because look what you can do now. So if you remember the multiplication of exponents with the same base, so if you have something like 2 to the 5th times 2 to the 7th, then you know that this is going to be equal to 2 to the 5 plus 7, which is going to be 2 to the 12th. So you know that you can, when you're multiplying exponents with the same base, you can add the powers. Same thing with going the other way around. If you have 2 to the 12th, you can break that up into 2 to the 5th times 2 to the 7th, or 2 to the 5 plus 7, however you want to write it. You can break that up if you want to. So here we have 4 as our power. So we can actually break this up to 2 to the 2 times 2. And I said plus here, you could have done plus, and I was thinking the wrong thing. You actually want to do multiplication here, because what you want to do is say 2 squared squared. And the reason why you want to do it that way is because you're looking for perfect squares. So you want this squared to be on the outside. So yeah, so ignore this is true, but that's not really the point I was looking for. I was looking for 2 to the 5th, 2 to the 2 to the 5th cubed would be the same thing as saying 2 to the 5th times 3. In other words, 2 to the 15th. This is the example I was going for here. This is also true, but not really what we're going to be using here. So same thing here. If we start at 2 to the 15th and work backwards, we can say 2 to the 15th is the same thing as 2 to the 5 times 3. And then even further, go do it like this. So because we want something squared, because this is going to be a perfect square, so we want something squared. Now we have something squared. We didn't start with something squared, but now we do have something squared. We have 4 squared. If we compute this 2 squared, then now we have 4 squared. And now we're back to the perfect square. All right, so same thing with this. So we have this 2 squared and 3 squared. So we know that this is the same thing as saying 2 times 3 squared. We've done that in previous sections. And now we can just compute the parentheses, and we know that this is going to be 6 squared. And we know 6 squared is 36. Okay, same thing for this one. Let's do 3, and then break this out into 2 times 2, which is going to be 3 squared squared, which is going to be equal to 9 squared, and 9 squared is indeed 81. And then one more. So 2 to the 4th is going to be the same thing as 2 to the 2 times 2. And now we also have our 3 squared. Okay, so what do we do here? Well, we can extract out this squared here from each of them. We're still left with the 2 squared though. So we have 2 squared times 3. And then we extracted out one of these 2's here. So this entire thing becomes squared. So now that becomes 4 times 3, or 12. 12 squared. And 12 squared is 144. Okay, so now what positive integer squared equals 96 times 486? So for this one here, you might not know how to go about doing this, but you know that this chapter is talking about prime factorization. So maybe give that a shot. Maybe start with prime factorization and see where that takes you. Whenever you have a problem like this where you don't really know where to start, just start doing something. Just start doing what you know, and then a lot of times if you just start doing something that you do know, then the answer will sort of reveal itself. You'll figure it out as you go. So just go ahead and get started doing something, even if it's only, well, let's just start with prime factorization because that's what we're working on. So go ahead and start with that and see if you can figure out this problem. All right, so let's do 96 first. So 96, and we're looking for a positive integer squared, kind of like I was going over here, where we're finding what squared is going to be whatever this is. So let's go ahead and do the prime factorization for 96. Let's see, so 96, this is a multiple of adding these digits together, will give us 15. So we know it's a multiple of 3. So let's do 3 and 32. Oops. You can also do, it's also an even number, so you can do 2 instead if you wanted to do that. And that would be 48, I believe, 2 times 48. So anyways, so we have 1 prime here. 32, let's see, we have 8 times 4, or we have 16 times 2. Let's do 8 times 4. And let's do 4 times 2, and 2 times 2, and 2 times 2. All right, so for 96, it looks like we have, I'll go ahead and circle these. 1, 2, 3, 4, 5 2's, so 2 to the 5th times 3. Okay, that's for 96. How about 486? 486. All right, 6 plus 4 is 10, plus 8 is 18, so it's not a multiple of 3. Oh wait, did I say 18? It is. So it is a multiple of 3 and 9. But I don't know what 486 divided by 9 is. Let's just give it a shot. 486. We know it's a multiple of 9. So let's see. 48. Let's see. Well, we can do 45, right? 9 times 50 would be 450. So leave us with 36 plus another 4. So we've got 9 and 54. Okay, 9 we know is 3 times 3. 54. Let's see. We can do. Let's just do 2. 2 goes into 5 twice. 27. 27 actually might be a prime. Oh, no, it's not. Wait. No, it's not a prime because 2 plus 7 is 9, so we know it's divisible by 9, and it indeed would be 9 times 3. 9 times 3, 3 times 3, 2, 3, and 3. All right, so 46 would be, how many 2's do we have? Only one 2, okay? 2 times 1, 2, 3, 4, 5. 3 to the 5th. Okay. So now that we have that all broken down, now we can combine these. So we know that this is 96 times 486. So we have 2 to the 5th times 3. That was our 96 times 2 times 3 to the 5th. Okay, well now we can combine some of these because we know 2 to the 5th times 2, and we can do that because multiplication is commutative. 2 to the 5th times 2 is going to be 2 to the 6th. And 3 times 3 to the 5th is going to be 3 to the 6th. Okay, so now that we did the prime factorization, does that help us at all? Did we do all that work for nothing? Does it actually help us with solving the problem? So what was the problem? What positive integer squared? Okay, so we're looking for a positive integer squared. Well, I don't see anything squared here, but we do have 2 to the 6th. So 2 to the 6th we know is the same thing as 2 to the 2 times 3. And 3 to the 6th is the same thing as 3 to the 2 times 3. And we know 2 to the 2 times 3 is the same thing as 2 cubed squared. And this is the same thing as 3 cubed squared. Okay, well now we have the same power here. We have 2 things squared, so we can pull that out here, do it down here. Now we know we have 2 cubed times 3 cubed, all squared. Okay, so now we have some integer squared. That's exactly what we're looking for, like a positive integer squared. Now we just have to compute it to see what the positive integer is. So 2 times 2 is 4 times 2 is 8. So we have 8 times, what's 3 cubed? 3 times 3 is 9, times 3 is 27. So 8 times 27 squared. And if we were to compute this, we would find that this is 216 squared. So that is our answer. What positive integer squared equals this number? It's 216 squared. Again, there's a video right here. Go ahead and check that video out. Very similar to this problem. All right, Paul multiplies 2 positive integers and gets a product of 16,000. If neither of Paul's integers ends in a 0, then what is the sum of Paul's integers? All right, so he has 2 integers that add up to 16,000, and neither of them end in 0. So it's not like he has 16 and 1,000. That's not going to work because one of them ends in a 0. So let's go ahead and, once again, I don't really know where to start with this, so let's just go ahead and start with prime factorization. So if we have 16,000, we know that that is 16 times 1,000. All right, so 16 we break down to 4 squared, or in other words, and 4 squared would be 2 squared twice. So it should be 2 to the 4th. Let's go ahead and break it down anyways. 4 times 4, 2 times 2, and 2 times 2. So that would be 2 to the 4th there. And how about over here? We have, well, 1,000 is 10 cubed, right? We have a 1 and then 3 zeros. That's 10 cubed. Well, 10 cubed is the same as 5 times 2 cubed, which that's going to be the same thing as 5 cubed times 2 cubed. So different way to do this. I know that's not exactly a factor tree, but it's another way to get to the prime factorization if you want to try it that way. So what do we have here total? We have 1, 2, 3, 4 2's here and 3 more here. So we have 2 to the 7th times 5 cubed. All right, those are both primes. All right, so now we have 2 to the 7th times 5 cubed. Well, what are these numbers? Well, 2 to the 7th, if we were to multiply that out, we would get 128. And 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. That would be 7 2's. 5 times 5 would be 25, times another 5 would be 125. And neither of them end in a 0. So 128 times 125 we know would be 16,000. If neither of Paul's integers ends in a 0, then what is the sum of Paul's integers? Well, what's 128 plus 125? Let's see, we have a 3 here. We have a 5 here and a 2 here. It looks like 253 would be our sum. All right. Okay, this one's a little bit tricky also, but let's see if we can figure this out. So let n be the product of the 10 smallest prime numbers. Explain why the prime factorization of n plus 1 must include a prime that is not among the 10 smallest prime numbers. All right, let's do this one first, and then we'll move on to B and C. So n is going to be the product of the 10 smallest prime numbers. Now, what are the 10 smallest prime numbers? Well, I have them right here, so I'll tell you. It is 2 times 3 times 5 times 7 times 11 times 13. Not that this really matters, but I'll write them all out just in case you're curious. Times 17 times 19 times 23 times 29. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's what our n is going to equal. It's going to equal this. It's going to be a pretty big number, right? Multiplying these all together, that's going to be a pretty big number. But that's what n is equal to, okay? So now imagine we have this number plus 1. So n plus 1 is going to be this number plus 1. All right, well, so let's think about that. So first of all, let's think about this number here. Now, I don't know what this number is, but let's ignore the 2 for right now. What would we get if we multiplied all of these numbers together? We get some big number, okay? And I don't know if that number is even or odd, but we can see that it won't actually matter. So let's say the number, we know it's not 1,000, but let's just use the number 1,000, which is an even number. Let's also use the number 1,001, which was an odd number. So now whatever number this comes up with, we need to do a times 2 to it. Whether we do it first, whether we do it last, it doesn't matter because multiplication is commutative. We know that n is going to be 3 times 5 times 7 all the way up to 29 times 2. It's going to be doubled. We're going to end up doubling something. All right, and so if we double 1,000, we get 2,000. If we double 1,001, we get 2,002. And what you might notice here is that it doesn't matter if we start with an odd number or an even number or an odd number, we will always end up with an even number. So we know that because we have this times 2, because this number is going to be a multiple of 2, we know that n is going to be an even number. All right, so how does that help us? Well, if we know that n is an even number, what does that mean about n plus 1? N plus 1 must be an odd number. And if n is an odd number, what does that mean it's not divisible by? It means it's not divisible by 2. All right, so now we know that n plus 1 is not divisible by 2. So 2 is not going to be a prime factor because it's not divisible by 2. Now, let's say that, what's our 3's divisibility test? Let's say 66. Okay, we know that that's a multiple of 3 because if we add these digits together, we get 12, and 12 is a multiple of 3. So 66 is a multiple of 3. And we know that n currently is a multiple of 3 because 3 is one of the multiples here. So n is a multiple of 3. How about n plus 1? So if this goes to 67, well, now we add the digits up, and that's 13, and that's not a multiple of 3. So now we know n plus 1 is not divisible by 2, and it's also not divisible by 3. Well, let's say that our big number here ended in a, well, it can't end in a 5 because it's divisible by 2. Let's say it ended in a 0. So we had this big long number that ended in a 0. Well, now n plus 1 is going to end in a 1, which means it's not divisible by 5. So now we know n plus 1 is not divisible by 2, it's not divisible by 3 or 5, and we can keep on going. If it was divisible by 7, now n plus 1 is no longer going to be divisible by 7 or 11 or 13 or any of these numbers going up to 29. It will no longer be divisible by 29, for example, because if it was divisible by 29, now n plus 1 will not any longer be divisible by 29. So that means the prime factorization cannot include any of these prime numbers. Not only must it include a prime number that's not among the 10 smallest prime numbers, all of the prime factorization cannot include any of these prime numbers because we know it's not divisible by any of these numbers. So we can't factor it into any of those numbers. So that's how we know that. If you're curious, by the way, in this in this scenario, n was equal to 6, 4, 6, 9, 6, 9, 3, 2, 3, 0. So this really big number is what was the product of all of these prime numbers. And then plus 1, it would just end in 31 instead. So in case you're curious what that number would have come out to be, it's 6.5 billion approximately. Okay, and the prime factorization, if you were curious about that, would end up being 331 times 571 times 34,231. 231. If you multiply those all together, you would get this 6.5 billion number. So again, a computer was used to generate these primes. This would be a very difficult thing to do by hand. So anyways, now let's go on to B. Let n be the product of the 100 smallest prime numbers, not just the 10 smallest, but the 100 smallest prime numbers. Explain why the prime factorization of n plus 1 must include a prime that's not among the 100 smallest prime numbers. Well, same exact thing, because we start with these first 10, and then we continue on to do the next 90 primes, but we know when we shift it, when we do n plus 1, it's no longer a multiple of anything leading up to that point. So it's not going to be a multiple of 2 or 3 or 5 or 11 or 13, all the way up to 29 and beyond, all the way to the first 100 primes. It won't be a multiple of any of those anymore. So then it's going to end up being a multiple of primes that are higher than the first 100. And in case you're curious about that, I'm not going to write out this number, because if you can imagine, if the first 10 primes, the product of the first 10 primes was 6 billion, you could probably imagine how big the number would be for the first 100 primes. But in case you were curious, it would be there we go. Let me move this up here. It would be this number right here. That's the number that you would get for multiplying the first 100 primes and then adding 1 to it. So yeah, go ahead and do the prime factorization for that. I'll see you in about 20 years. Okay, so C is, let me go ahead and delete this off here. All right, so C is explain why there's not a largest prime number. That is, explain why there are an infinite number of primes. Okay, so if you can come up with an intuition, an understanding of why it might be the case where there is no such thing as like a last prime number. It might be hard to think about why, like how you could prove that. So if we think about it, and let's say that we have some finite list. By finite, I mean it ends somewhere. There's a certain number. Let's say there's, let's say that you found the 10,000th prime number, and you think that's the last one. I found prime number 10,000, and that's the last one. Let's just pretend that you think that. Well, if you made a product of the first 10,000 prime numbers, which that's going to be a gigantic number, an unimaginable number, right? If you multiply together the first 10,000 primes, it would be a multiple of all 10,000 of those primes. So now imagine you come up with a number. Even if that number is unimaginably big, it's not infinity, right? It's an actual number, even if it's a very, 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 very large number. It's going to be a number, and it's a number you can add 1 to. So if it's a number that you can add 1 to, now when you go to get the prime factorization, now you know that there must be another prime in order to factor that. Even if adding 1 is the next prime, and the prime factorization just is that gigantic number, that still means that there's another prime. So even if there are no other factors of that gigantic number, that means that that's another prime. So no matter how you try to think about it, you know that if you come up with a finite number that is not infinity, even if it's an enormously big number, then you can add 1 to that number, which means that you need a new set of prime numbers to factor that. So that's why there is no such thing as a largest prime number, because you could always add 1 to whatever number you can come up with. No matter how big the number is, you can always add 1 to it, unless that number is infinity. And in that case, you're not talking about a finite set. All right, and that's it. So go ahead and do these 3.4 exercises. Hopefully this lesson wasn't too bad. I know it was only a few exercises, but some of them I took a little while to explain them, but hopefully this is at least semi-interesting. Go ahead and do these exercises, and I'll see you next time.